we can spend all the time trying to take the most perfect picture and then something comes out of nowhere and ruins it for us. So what are we trying to do when we're generating digital images? So what we're trying to do is get the best representation of what we're seeing down the eyepiece in our actual image. Now the rule is if you put crap in, you should get crap out. Unfortunately, if you know what you're doing, or conversely don't know what you're doing with microscopy setups, you can make data that looks pretty crap look pretty good, or data that looks pretty good look pretty crap. So some rules to try and look at is to not use offset on your raw data. So offset is a setting where you can clip the lower end intensity values from your image. You should set your ranges that you're acquiring your data on using both positive and negative controls. And if you want to be able to compare the data, then acquire each different set with the exact same settings. And one really important thing is to do a pilot analysis before and during your imaging. So am I getting the data that I want from my actual experiment? Once we've acquired our data, we can look at it on something called an intensity graph. So we've got two examples of an intensity graph here. On the x-axis, we're looking at the intensity, so you can see the intensity graph on the top is running from 0 to 255 grayscale values. That's an 8-bit image. And the one below is going from 0 to 65,000. That's a 16-bit image. And on the y-axis, what we're looking at is the number of pixels with that intensity. So over here, this is the lower end, this is the black background within your image, and the further we stretch out up here, these are the brighter sections within your image. Now it's really key when we're acquiring our data that we avoid saturating the detector. So we want to be able to quantify and visualize everything that's captured on the image. And a lot of microscopes nowadays have intensity range indicators or special lookup tables which will show you when you're hitting saturation. So in this example here, we've got red pixels showing up, and also in the histogram you can see over here that the data is hitting that maximum value as well. What we ideally want is an image that doesn't have saturated data, and again you can see that within the histogram that it's not hitting this maximum value. If we are getting saturation, how can we deal with that? Well, we can decrease the excitation percentage, so how much light we're putting on to excite our fluorophores. We can decrease the camera exposure time if we're using a camera-based system, or we can do things like increase the scan speed if we're using a confocal, or decrease the gain if we're using a confocal or a camera that has a gain setting on it. Next thing, if you remember, we were talking about our pixels have a set size, and that's because when we're creating a digital image, we're creating what we call a raster image. So our image is broken up and the intensity is assigned into these pixels. This means that sampling is set, so if you try and zoom in on this little blue duck, it's only ever going to get more pixelated. So that's the raster image. The vector image on the right is something that you might create in something like Photoshop. This is where all of these curves and angles are mathematical formulas, so if you zoom into them, then they will scale and won't become pixelated. So the key thing is when we're taking our microscopy images, we're generating a raster image, we're setting those pixel dimensions at the time of acquisition. So the question is, what size should our pixels be when we're trying to capture that data? So what we're going to do is we're going to take our blue duck and we're going to divide it up into pixels, and then your job is to try and work out at which point you're happy that you can see a blue duck. Now normally I ask for a show of hands in our workshops, but it's going to be a bit difficult in this case, but hopefully no one can think that they can see a blue duck in the 3x3 frame size here. By the time you get to 5x5, then you might have a little hint. By the time you get to 10x10, then you're probably a little bit more certain that that's an actual blue duck that's being represented in the digital image. And by the time we get to 20 by 20, then we're pretty sure that we've got a blue duck. But what now if the question is, can you count how many eyes there are on the blue duck? Would you be able to surely tell me that that was 1 or 2 eyes that you can visualize in that image? In that case, you might need to sample slightly differently. So the really key thing before you start to acquire your data is try and think, what analysis do I want downstream from this? What information do I really need? And then we can try and set the sampling to match the information that you're going to need downstream. So fortunately this is covered by some mathematics. So this is called the Nyguist rate, or the Nyquist-Shannon sampling rate. And what this says is basically to optimally represent an analog signal in digital space, the analog signal needs to be sampled at least 2.3 times. Now we've shown this in this little these waves. So the blue wave is our analog signal, and the red line is our digital sampling of that. So at 0.83x, you can see that our red line is not representing the analog signal, the blue line. By the time we get to 1.3x, we're getting closer, but again, we're probably not there. In this case, we'd call this undersampled. By the time we get to 2.3x, it's not perfect, but it's pretty close. By the time you get to 10x, it looks much, much better, but in this case, we're probably oversampled. So 2.3x is the magic number. I can't do that maths, so I always round it up to 3. So basically, if you know the structures you're interested in, to sample it correctly, you need to divide the size of that structure by 3. The downside with oversampling is if you're on a confocal, it's going to take a long time to acquire that data. Okay, so fortunately there are online calculators which allow us to calculate these numbers, and also a lot of the acquisition softwares now have an optimum button which also allows you to set your sampling rate correctly, so your pixel sizes correctly to get the best resolution. The table that I've put up on this slide shows the recommended pixel dimensions if you take the theoretical axial resolution and divide that by 2.3. So if we look at the bottom, for example, the 63x and the 100x objectives, which have a 1.4 NA resolution. So if you remember, numerical aperture is what's giving you the resolution of the system. In the green channel, you're looking at 60 nanometers pixel sizes to get the best possible resolution out of that microscope. Now there are a couple of caveats here. First of all, it's working off a theoretical axial resolution, and that assumes a perfect optical system. Let me reassure you that your microscope is not perfect. So I'd be suggesting somewhere in the order of 60 to 80 nanometers if you want to sample correctly to get the best possible resolution on a microscope with a 1.4 NA objective. Obviously, if you're using super resolution techniques, then this would also change the pixel sizes that you need. The other thing to bear in mind is this is only if you need the best possible resolution. If you're counting nuclei, then pixel sizes of 60 nanometers is dramatically oversampling what you actually need.